Welcome to the course Business Analytics and Data Mining Modeling using R Part 2. So, in previous few lectures we have been discussing cluster analysis. So, specifically in the previous lecture we stopped at this point and we wanted to discuss Watt's method. So, which is also part of hierarchical agglomerative clustering approaches. So, let us start our discussion with this particular method. So, as I said, Watt's method is slightly different from what we have discussed so far, other approaches that we have discussed so far within the HAC hierarchical agglomerative clustering methods. So, how it is different? So, let us see. So, the main point of difference is mentioned here in the slide, that instead of finding two closest observations to form cluster, this method selects the cluster formation which results in smallest incremental loss of information. So, as you can see in other methods and the distance matrix that we use in HAC, we typically look to identify the two closest records and later on two closest clusters to build our clusters. However, this particular method, Watt's method, it actually selects the cluster formation. That means the clusters which are formed, the clusters which in comparison to the previous formation, in comparison to the previous steps, it tries to minimize the loss of information, right. So, a new cluster formation is going to replace the previous the cluster formation. So, whether there has been a loss of information, and to minimize that loss of information is the main idea behind this particular method, Watt's method. So, let us discuss further. So, few more details about Watt's method. So, you can see here main idea being that merging of observations to form clusters can be thought of as information about an individual observation being replaced by the information about the cluster where it will be merged. So, we can think about an individual observation which will be representing a certain piece of information, and when it becomes part of the clustering process, when it becomes part of some cluster, then the information its information is going to be replaced by the information about cluster. So, because of this there could be some loss of information. So, that is measured and then minimized in this particular method. The same points are being conveyed here. Now, how this loss of information can be measured? So, the metric, the popular common metric that is typically used is mentioned here, error sum of squares, ESS. So, what it does? It measures the difference between individual observations and a group mean. So, when a particular observation becomes part of a cluster, then of course the cluster mean is that group mean might be representing the information about the cluster. So, the difference between this individual observation and group mean, so that is being measured by error sum of squares. So, let us understand this whole thing with a simple example that we have in this slide. So, let us consider following univariate data. So, 10 observations, one variable. So, we have 10 observations that we want to cluster, and then we have just one variable, right. So, these values could be, so values for this particular just one variable could be this one 2 6 5 6 2 2 2 2 2 and then 0 0 and 0. So, these are the 10 observations that we have. So, if we look for the mean value of these observations, that is going to be 2.5. So, if we cluster all of these observations into a single group, right. So, a single group, so this group will have a mean value of 2.5. So, all these observations, instead of representing their individual information, now they are going to be represented by this mean value, because they are going to be part of this cluster, right. So, how we are going to apply this particular metric, error sum of square, that we talked about. So, loss of information can be computed in this fashion. For first observation, you can see 2 minus 2.5. This is square of this value, then for second observation 6 minus 2.5 is square, then for third observation 5 minus 2.5 is square, and so on. So in this fashion we can compute the error sum of a square, which comes out to be 50.5. So the loss of information can be expressed using this particular number in this fashion, this metric error sum of square, and this is the loss of information that we have. However, as I said, we had 10 observation, and we wanted, if we wanted to club them in one group, and that group mean we understood, and we calculated the ESS value. Now let's change this cluster formation. Now if we want to cluster these observations into following 4 groups. Now you see the first group containing all the values which are 0, then the second cluster containing all the observations which are having value of 2, and then this singleton cluster having just one observation of value 5, and then 2 observations 6 of having value 6, right. So we have these 4 observations. If you look at the clusters, this particular cluster configuration, you can see we are clubbing all the observations which are having the same value. Therefore their mean value is also going to be the same. Now we have 4 clusters right now, and if we apply the same formula ESS here, then our ESS value is going to be come out to be as 0. So therefore loss of information as per this metric is going to be 0. So probably the next step in this particular method, Watts method, is going to be this one. So these observation, if they are the cluster analysis using the Watts approach is to be applied, then probably this is going to be the next step, because the incremental loss of information is minimal in this particular cluster for this particular cluster formation. So you can understand how this is this approach is different from the earlier approaches. So in the earlier approaches under HAC that we talked about, we look to identify the closest observation so that we can create a cluster, right. Here in this case Watts method, we look to identify a cluster formation which is going to have the minimum loss of information as per the metric that we are going to use. Few more important points about Watts method. So for example, the kind of shapes that are produced, the shapes of clusters, produced clusters. So we can see here tendency to form convex clusters of approximately equal sizes. So why this happens also you can easily see from the previous example that we have discussed. So in the previous example we saw that the particular cluster formation which were combining value, which were combining observation with the same values. So there the loss of information was 0. So therefore from that observation we can see that this particular method would actually lead into convex clusters, and the sizes would also be approximately roughly might be equal. So where this particular kind of method could be suitable. So for example, employee performance ratings, students grades, customer segments. So these are some of the problems, some of the areas where this particular method can be applied and could be more suitable, because the way the performance ratings happen, the way grading happens, and sometimes we might also want to have customer segments of equal sizes, and which are we would look to minimize the loss of information as advocated by Watts method, then this is more suitable approach. Till now under HAC we have discussed the more common approaches. Now after discussing how the clustering happens, let's understand few more details about the cluster analysis. So how the clustering results are displayed. So in this particular technique also, just like in the classification and regression trees that we discussed in the previous course, we have a tree like diagram here which is called Dendogram. this particular dendrogram, this particular tree diagram or structure is actually used to display the clustering results, and it also in a way summarizes the clustering process. How it does this particular thing, we will see in this lecture. So, before we move ahead, let us understand this particular this particular graphic dendrogram. So, what this is about. So, in dendrogram, this is a tree like structure. So, we will see when we do an exercise in R, we will see how this dendrogram looks like, but to start with it is a tree like structure, tree like diagram, and the bottom level of this particular dendrogram, this particular tree like structure are going to represent all the observations, because we are talking about right now, we are talking about the HAC, hierarchical agglomerative clustering, where we start with all the observations being considered as clusters, right. So, bottom level of the tree is going to represent all the observations. When two observations are merged, vertical lines we will see that through an exercise in R, that vertical lines will represent the distance between the observation which are going to be merged, and then they would be depicted to join together. So, we might have at the bottom level we will have a certain number of observation, and depending on their distance, if they are found to be closest, they are going to be merged. So, that in the tree diagram you would see that joining happening, and that is how this tree structure is going to be created bottom up, right. So, because of this bottom up process, all the observation, then joining, and then this structure will keep on building till we end up with just just like in tree diagram, just one node. So, where in this case we say just one cluster having all the observation. So, the whole process would also be depicted in this particular diagram. So, it can also be used, this dendrogram can also be used to find out the number of observations in each cluster if number of clusters to be created is specified. So, if we have certain expectation that the number of clusters in a particular data set, in a particular problems are required to be 6 or 5. So, this particular dendrogram, this will also allow us to get those number of clusters, and will also able to see through this dendrogram which are the observation which are going to be part of these clusters. So, for each cluster we will get to know the observation which are going to be part of those clusters, and how those clusters are going to be created. So, all that would be clearly visible in this particular graphic dendrogram. So, let us open our studio, and we will do a small exercise to find out more about what we have discussed. So, let us go through some of the code that we have understood in previous lecture. So, let us import the data set. So, few lines of code we will just go through, so that we are able to reach to the point what we have discussed so far. So, all these lines of code we have discussed in previous lecture. So, we won't discuss them, we will just go through this part of code, and we will just run through some of these things. So, in the previous lecture we had gone through this. So, where we created where we computed the centroids for 2 clusters. So, all this we have gone through. So, let us quickly go through this. So, this part also we covered, where we can see how two observations were merged and how the distance matrix were computed. Now, we have reached to this point. So, till now in the previous lecture, the exercise that we have been doing, we selected 5 serials from the data set that we have. Out of 35 observation, we picked up first 5 observations, first 5 serials, and we went through an exercise in R and we applied our hierarchical agglomerative clustering. Now, what we are going to do is we will use a full data set and see how some of these approaches, HIC approaches, can be applied. Right. So, let us have a relook at the data set that we have. So, this is the data set that we have. So, in this we can see the variables which we have discussed already, and so now in this because we are going to use all the observations here. So, we have 35 observations, 70 variables. So, as we have discussed in previous lectures, before we move ahead, we need to normalize all these variables, so that the scale dependency is taken care of, because typically we use Euclidean distance matrix. So, for that we need to normalize all the variables that we have, numerical variables. So, this is the code that can be used. You can see we are using a scale function. So, this particular function we have used before also in previous course as well, and so this will create the normalized scales for us. You can see first 6 observation, you can see the normalized values here. So, all the variables have been normalized. Now, with this we can compute our distance matrix. So, here we can we are going to have the distance between all possible pair of observations. So, we have 35 of them. So, this matrix 35 by 35 matrix is going to be created, you can see here. So, all the distance values have been computed. Now, to apply some of the methods that we have discussed so far, for example, Watt's method, single linkage, and other methods that we have discussed. Now we are going to apply each of them on a full data set. So, you can see we will start off with the Watt's method. So, here we are calling this function hclust. So, this is for hierarchical clustering, and in the first argument is first argument is the distance matrix, a matrix that we have just computed. So, this distance matrix is going to be used for further processing and implementation of these different HIC approaches. So, first one, we are starting with the Ward approach. So, there are 2 versions which are available in R. So, this is the more latest version which we are going to use here. So, let us run this code. And once this model has been built, we can plot this using plot function, and some other arguments have also been specified, and we will see the dendrogram for this particular model. So, the 35 observations that we have, all the observations that we have in the data set, and all the variables, 17 of them have been used. They were first normalized, as we just saw, and now we are we have just built the model. Now, we are going to see the output using dendrogram. So, you can see here the dendrogram. Now, this particular dendrogram has been created using Watt's method. So, you can see all 35 observations, all these observation at the bottom level, they have been they have been indexed. So, their names you can so those IDs you can see, observation IDs you can see here, and so this is on x axis, and on y axis we have the height. So, that is going to display at which point these observations have been merged. So, these heights are also indicating the relative relative occurrence of these joining or mergers. So you can find out probably which observation were merged first. So from this visual inspection, if we are correct, so it seems that observation 3 and 11 were merged first, right. So you can see here the same thing you can also verify using the distance matrix. So in the distance matrix, if you see that the distance between these two observation 3 and 11 happens to be the minimum distance, then probably what we just saw through this dendrogram was correct, because there are a few other observations also which are also having very small height. So we can see, for example, 26, 27 and then the observation 19 and 24, they also seem to be merging in the initial part of this clustering process, but it seems that 3 and 11 this merger happened first. So as we talked about Watt's method, so instead of finding two closest observation, we look to compare the cluster formation, the previous one and the new one, and try to minimize the loss of information. So using this approach, this particular cluster, this particular dendrogram has been created. Now using this dendrogram, as you can see, you can see the clusters are nested, right. So eventually we end up with one cluster, but if we go down from the tree, then we can see the nesting of clusters. So if we are going for example, if we want 6 clusters, then we can all the time we can draw an horizontal line here. So we can draw horizontal line here, and in this particular graphic, and the intersections, the line will intersect this particular dendrogram at certain points, and those intersection points will give us the equal number of clusters. And if this particular line we go up, then the number of clusters are going to be fewer. So we might have from 6 to 3, just 3 clusters. And but interesting thing that is we would find that the clusters now would be nested, right. So let's go back. Now let's apply the other approach. This is a single linkage approach. So in the single linkage approach, as we talked about in the previous lecture, we look the distance between clusters, two clusters is computed using the minimum distance between pair of observation, one from each of those clusters. This part we have discussed. So we will just call this function hclust, and the method has been specified as single, and we will get this model, and then we will plot the dendrogram. So let's execute this. So this is the dendrogram for this approach, single linkage approach, and as you can see, this is quite different from what we have from Watt's method. Again, here also we can clearly identify which two observations were merged first. So it seems that 3 and 11. So if you remember that in Watt's method also, these were the two observation IDs that were merged first. So 3 and 11, so these observations seem to be merging first. So from this we can see the approach is different. We are just looking at identifying two closest observation, and then two closest clusters, right, and in this fashion this particular clustering process happens. So let's go back. So as we talked about for Watt's method, if we want to have if we have this that we need 6 clusters out of our clustering process, then you can see here the example number of desired cluster 6. Then what we can do is to cut a single linkage dendrogram into 6 clusters. We can call this function cut tree function. So here we just need to pass on the model object and the number of clusters that we desire. So this particular function is going to cut the model into these 6 clusters. Then we have another function rect.hclust, which can actually redraw the dendrogram. If we want 6 clusters, so those this particular dendrogram is going to be redrawn, and we can create the borders to see which observations are going to be combined in particular clusters. So, let us run this part of the code. So, this groups is just for the cutting the single linkage dendrogram into 6 clusters. So, you can see here all the 35 observations. You can see in the environment section groups variable has been created. We have 35 observations, and we are looking to if we are interested in looking at the values, then we can just type this. We will just run this. You can see the observations in the output. You can see the observations and their cluster ID. So, which cluster they belong to. So, we created 6 clusters and how they have been assigned. So, any single any dendrogram that we might have, we can cut it as per the requirement of the number of clusters, and using this Perker function we will get the cluster IDs. Now, if we want to visualize this process, then we can call this function rect.hclust. So, let us run this. You can see here this particular dendrogram. You can see red borders here because we had specified this red color, and we can see here how these 6 clusters have been formed. So, you can see the cluster in this region, in this right part of the region is the biggest cluster having most of the observation. Then we have the next cluster is this one having 2 observation. Then we have this cluster having 3 observation. Then we have 3 cluster with just 1 observation. So, if we want 6 clusters, then this is how these are the cluster that we are going to have, and we can easily see the observations which are going to be part of each of these 6 clusters. So, the process, the results are very clearly they can be very clearly understood using this particular dendrogram. Now, we can also apply average linkage approach in HAC. So, the same function. Now, hcclust the same data matrix that we have computed, and method we have to just specify average, and we will get there. So, let us run this. Now, we can again plot this one as well. You can see a new dendrogram has been created. Now, this was created following average linkage approach. So, here you can see the way this dendrogram, the way clusters have formed, the clusters have been merged, observations have been merged, is quite different from the previous 2 approaches. So, if we just go back and do the same thing, if we are interested in having 6 cluster, then again we can call this function rect.hclust and run this, and we will again see how these clusters are going to be identified. So, you can see here in the leftmost cluster we have 3 observations, then the second cluster in the middle, this is the largest cluster that we have, more number of observation, most of the observation in this cluster. Then we have one more cluster with high observation, and then 3 cluster with single observation. If you remember in the previous output that we had, these 3 singleton clusters were there even in the case of single linkage method, and even in the average linkage method these 3 clusters can be clearly seen here, right. So, in this way we can easily apply hierarchical clustering approach in R, and we can see through an dendrogram how the results are going to be and how the clustering process has happened. All this can be clearly seen. So, we will stop at this point, and in the next lecture we will continue our discussion on cluster analysis. Thank you.